So good morning to everybody. So today I will discuss more the prior, the hidden Markov non-parametric prior, which has the nice thing as we stopped on that to be able to handle non-parametric emission distributions. So to start, well, what will I do today is first discuss non-parametric inference of hidden Markov models, but I will start with some reminders about ideas and methods in non-parametric inference. Then I will focus on hidden Markov models to say how you can manage to use them for hidden Markov models. And in a second part, I will, well, am I allowed to... Il est où, Julien? Julien? Je peux enlever mon masque, moi, ou pas? Ouais, je suis assez loin. Maybe it's better. In the second part, I will talk about the fundamental limits, because as soon as you are no more dependent, then you are no more identifiable. You remember maybe you remember the proof where you needed the transition matrix to be full rank, and if it is not, you can not use the trick, and even you know that non-parametric mixtures are not identifiable. So, of course, it's not only at the point where it is not IID, since you have finitely many data. So it's important to investigate how much you can be close to the IID limit to be able to do things. So this will be the second part of the talk, and so we'll study it in the simplest setting of hidden Markov models, and it will give me the opportunity to remind a very important idea in statistics about how to prove lower bounds. So first, just to recall where we stopped on Tuesday afternoon, we've seen that if you use enough consecutive observations, then the model is identifiable. And then if you use them in your estimation method, then any estimation method you should work to reconstruct all parameters of your hidden Markov model. And how does it work? So let me now recall things about non-parametric estimation. So I will first recall frequentist ideas, because this is where it started in the late 70s, I think. First, people tried to understand how to do adaptive minimax estimation of density. Of the observation. So not of any inverse problem, but just of what you observe. It was known, well, it's known in those years that the rate depends, let's say, on the smoothness. And if beta is the smoothness, then you may know that the rate depends in general this way on the smoothness. If you have one-dimensional observations, then in the reconstruction method, I will mention two classes of methods. Kernels, where you have a smoothing parameter that you have to choose depending on beta. And if you do basis expansions, such as Fourier, and also in those years, mathematicians discovered wavelets. The truncation parameter has to depend also in the smoothness. And the main thing was to understand how to be able to choose beta on data to do to get adaptive rates, adaptive estimators, for which the rates stays true whatever beta, the smoothness of your density is. And then started, it was a bit later, so those were mainly asymptotics. And then started the model selection story. In which you try to do things non-asymptotically. And it's can be non-asymptotics. And then the main thing is to understand that you have, for instance, a sequence of sieves of finite dimensional. When you make truncation using basis expansions, you truncate your basis expansions, which means that you have a sequence of models or a family of models, I would say. It cannot be, it can be not embedded. And to choose the model, you have to make a compromise between complexity, in complexity, such that you make a compromise between bias and variance. Since with low complexity, you have large bias. If you truncate with a small dimensional space, then you have a large bias. Your density is far from this model. And if you have a large model, a large complexity, then you have many, many parameters to estimate. Then you have large variance in your estimator. So the model selection thing is to make a good compromise between bias and variance. So one way to do, there are, I would say, essentially two families of methods. You can minimize something which makes the compromise. So this is for complexity. You minimize in the complexity something which is a proxy of bias and something plus something which is a proxy of variance. This can be penalized criterion, or this can be using the Lipski's method. Well, anyway, in all such methods, you have something like that. Or you can use some cross-validation IDs in which you split your sample and you estimate bias and variance this way, and you choose your complexity. So these were the main ideas in these years in the frequentist world, I would say. And then a little later, in the Bayesian methodology, people try to understand if it's possible to recover in the posterior concentration rates, adaptivity, and the same rates with adaptivity. And as you may know, well, I would here put the name of Ad van der Waart. I remember he visited Orsay. It was in the late 90s, and he's the one I believe so, who put the bridge between both worlds, and to understand how the prior, what are the conditions of the non-parametric prior to put on. So here it's something different. You have to put a condition on your nonparametric prior, and then you can obtain rates and adaptive rates. And here I will not mention so many details, but because I'm not so much an expert, even if I use them. And then the last thing, the last general thing I will mention is that even for the frequentist Bayesian world, very useful tool is deviation and concentration inequalities. I would say deviation also, but maybe concentration, in which you prove things like that look like you need to understand how empirical means deviate from something, and you understand it uniformly for classes of functions, and such inequalities. Here, I would do it like this way. So you have some term depending on the complexity, some term depending on the variances on your class, and something depending on how large can be the functions. So this is one key tool that people use to prove, to see how even the likelihood behaves or anything. But then here, so I come back to my hidden Markov model. There is something here that shows up when you use dependent variables. Then there is something about mixing. You have to take into account the dependence of your variables this way. So now if I come back to my hidden Markov model, so I will speak again a little about the spectral method, in which it's not exactly the same story. We can have access directly to the parameters by inverting matrices, etc., etc. But in general, what you do for inverse problems, what you are able to do is to estimate the density of your observations using those ideas, all those methods that may be difficult, but you know how to do. For instance, likelihood or least squares or Bayesian method. It all works on the distribution of the observation, and do some model selection. And then you have to go back to your parameters. So when you consider the transition matrix, so it's possible to, I will not say how to estimate. So when I'm back to a hidden Markov, I consider here for the first part J hidden states that may be more than 2, and the transition matrix of the hidden Markov will be Q again, and the emission distributions or F1 to Fj, and you know those works, we assume some dominating measure and densities, but you don't need it for the identifiability trick, but anyhow, so for the matrix Q, which is parametric, which you have finitely many parameters to estimate, then it's possible to get efficiency that is the best asymptotic variance. That was part of the talk of Judith, where she explained how to get efficiency for this using both frequentist method and Bayesian method with this cut prior, which is a very nice idea to do both together. Then if you want to go back to the emission densities. So here, what you are able to prove using all those ideas about nonparametric estimation, you're able to prove things in the direct problem of the form. Then you get an upper bound for the supremum risk over some class. So it's about the transition matrix over some class. You're able to bound the criterion, the distance between your observation of, well, maybe 3 or m, I said m, that you use after to identify. So it could be maximum likelihood, or it could be least squares, where you model using hidden Markov modeling your distribution of m consecutive observation, and then you get something like that with rates and things like that. But then you want to go back to something about the distance between your parameters and their estimators with some distance. So this is, and then to do this, what you can try to do, so that's what we've done, and that's what also Judith talked about in the Bayesian story. You go back by lower bounding this criterion by something about your parameters. So this is what I mean about requiring a quantitative inversion when using your nonparametric method, whatever your nonparametric method is. So with all the people I mentioned doing their photos at the first talk, we've been able to prove results about the L2 risk of the emission densities. It was possible to do it globally by such method, and it is possible to have the adaptive rate individually for each emission density, but this requires to use a more precise selection for each emission density. And in the Bayesian world, the result is about the L1 risk. So maybe we can use your we can use your L1 inversion to put it also in the other story to get adaptive rates for each emission density. And then when you recover your parameters, you can compute the posterior probabilities of your hidden sequence. And the question was to understand the propagation of errors, and I shown some inequality about that, but we proved where you upper bound the errors on the posterior probabilities with the error on your estimation. And the last key point, about which I think the story does not end, is not finished, is about misspecification, because of course hidden Markov models are an idealized vision of dependent sequences. Dependent sequences are of course not all hidden Markov, but so you need to understand what happens if you are wrong, if in fact your observations, the latent variables are not Markov and your observation are not exactly in your model, so there is some bias term in here. So here, instead of having this, you have a bias term, the distance to the model. And then there is some result in Luc Louis' thesis about that, but I believe there is much more to understand about that if you want to use all those ideas as as I said in the beginning, I use a very general idea to understand how dependence can help to have more flexible learning of anything hidden in your data. So this is a key point. So now about this non-parametric estimation, I come back. I thought I could not start with such things. This is why I started with the general ideas. So now we come to more specific equations. So maybe you remember how the identifiability proof worked. So if you assume that your emission densities are linearly independent, yeah, if they are linearly independent, then if you only look at 3 consecutive observations, then you can use the tensor trick and recover everything based on here the situation where you use only 3 consecutive observations. So how does it work? So you take so this is again the identifiability trick, but the way you can handle it using empirical means. So you take expectations of functions, product functions of 3 consecutive variables, and these can be estimated using empirical means, because you know how empirical means behave using such inequality in which you take care of here is hidden Q, the transition matrix, to understand the. And then the P, the matrix which is written P, is the situation where in M, in the middle, you take the identity function equal to identity. Then you invert the P, but of course, since you don't know with which functions you will have an invertible matrix, you take a large enough one which will have the rank you need, which is J, and then you take the singular vectors to make things invertible in the right dimension. Then you compute the matrix where you invert P. Think of V as something that allows you to invert P, and which is computable on data, because it's just something coming from the estimator of P. You have an estimated matrix. You search for singular vectors, you invert it, and then you compute your matrix B. And then at the end, you see that this matrix, this is the matrix B, you see that it is diagonalizable. The eigenvalues allow you to recover your function, all your function fj's, if you change your kernel k here to various functions. And one very important thing I didn't discuss on Tuesday is that here it does not depend at all on the k here. So if you keep always the same h's, by varying k, you don't change the eigenvectors. And this allows you to fix the label switching issue, because once you have distinct eigenvalues, then you can fix your eigenvectors, and it fixes the label switching issue. And by taking linear combinations of all those matrices, then once you come to separated eigenvalues so that you can fix the label switching issue. So this way you recover empirically, and using such inequalities, everything you want, and you are able to get adaptive estimators. So this is the more recent results we've got about it. It is about estimation in Subnorm, and this is what we needed for doing the multiple testing story, where we had this upper bound to handle about the posterior probabilities. And here you see that in case you have count data, so that you have a deliverable possible set of observations, then you get the parametric rate in Subnorm for your distribution. And how does it come? It just comes from the fact that you have some Glivenko-Cantelli trick that says that for the indicators of if you just look at individual values and your indicators here, that is, you count your observations in each cell, then there is a Glivenko-Cantelli result that says that it goes at uniformly in all those functions at parametric rate. And this allows you to get in Subnorm the parametric rate for this emission density. And then in the general continuous situation, for instance, by using kernels, but you also could use wavelets. That is, when you take your expectation and your empirical means, you apply to functions that can be kernels, that can be wavelets, and then you get the usual rates in Subnorm estimation on regularity classes. And well, all this works well. Yes. So you have a label switching issue that you fix in a sense that this one will not depend on n for n large enough. You fix it, but of course you don't know it. You don't know which one it is. I'm not sure I understand your question. Of course you have a label switching issue. If you do not have think about the one which is, for instance, the first population or the second, that you cannot fix if you do not have information about it. But you just have one way to fix it. So is it related to what I said before here? It's just because here, you know, you just estimate one kernel on the function. And if the permutation changes each time you change your kernel, you cannot recover a density because you will put for instance, some wavelet coefficients in F1 and then others in F2 and then others in F3. But you put, by fixing the eigenvectors, you put your, say we work with wavelets, you put your wavelet coefficients, once you fix them, always in the same density. Is it more clear? Of course, for the Bayesian multiple test, for the Bayesian multiple testing story I've told Tuesday, we need to know which emission density is the null and which one is the alternative. So, as I said, we have another criterion to decide, the one which weights more largest values or something like that. But else we could not. There is indeed something that cannot be fixed without extra information about label switching. So, hidden Markov models are very nice because they allow non-parametric modeling for mixtures on dependent data. You can make the machinery about non-parametric inference work and get the usual adaptive minimax rates for learning all parameters of the model. You can use the method, and then it's important to understand how you can use different methodologies in any word, frequentist bias, and then there is much work to do, but it works. There is a last question, which is there is an important question which is unanswered, which is about when you do maximum likelihood, how do you invert the callback rate? So we have no answer about that. But then, of course, when you have your data, you have good reasons to think they are dependent. For instance, you are looking at a place on the DNA, or you are trying to understand the time series in which you believe there is some dependence, or so you believe there is some dependence that allow you to have this very flexible model to do non-parametric mixtures and such things. But maybe it's not true. So what happens if, in fact, your data are not dependent enough so that your answer is meaningful? So now we'll talk about the second part of the story. That is, what are the limits? How close can you approach the limit of the independent data to have still meaningful results? So it is about Q being non-full rank, or the emission densities being not distinct, or if you stay in one state, then if you stay just in one state, then you always have independent observations. So to investigate these questions, I will discuss it specifically on the very simple situation where we have two hidden states. So here I changed the notation compared to the Bayesian multiple testing story. I changed the notation because theta will denote the parameter, and the hidden variables will be the x's, the x. And there will be binary, and the transition matrix will be Q. I keep the notation on the ball, so if you compute the stationary distribution in case it's possible, and then the observation of density F0 or F1, depending on the state X, and the parameter will be denoted by theta. So this is no more my latent variable. And the parameter, there is only little p, small q, and the two emission densities. So this will be the setting. And also, to fix the idea, I take multinomial emissions. That is the observation. Can take finitely many values. So, for instance, you have binary observations, and if they are dependent, if you model using hidden Markov, then you can recover two populations of Bernoulli, what you could not do if your observations were independent. So it's possible to do it if the parameters P and Q are not 0, not 1. If the determinant of Q is non-zero, that is when P plus Q is not equal to 1, and when the emission distribution are distinct. But you might be interested, and we are interested to understand, as I said, if we want to understand the frequentist bias story about sparse sequences and how you're able to have more power to recover latent structures that have some structures and block structures by using Bayesian method. In the sparsity sequence model, we are interested to understand what happens about sparsity. Sparse sequences occur when you stay long in one state. That is when sum of P or Q is small. Also, you can be interested, and we are interested in understanding how much separation you need to be able to recover the populations. Because, of course, if you just have one population, you don't recover two populations. They have to be distinct. But we hope that they have not been to be so far away as in the independent case to recover things. And also, because this was the discussion at the beginning, it's about dependence. You want to understand how they have to be dependent, so how much P plus Q has to be different from 1. And we want to understand that on finitely many data. How is learning impacted when you are near the limit cases? So this is the question of the fundamental limits of the learning of hidden Markov models in these situations. So in fact, how can we answer the question? But by understanding, in the previous slides, I've shown rates. But of course, in those rates, what I didn't say is that there are constants in front of the rate, and the constants depend, in fact, on the model. So there was this supremum for QF in something, but I didn't say that the constant on the right-hand side of the inequality depended on the model I put on this, and the model, of course, depends on how far you are from the boundary. So here, the boundary will be, so I take some, so there are three things I will handle together. The distance to sparsity. The distance to sparsity will be named delta. Which is positive. The distance to independence is about the determinant of Q and will be named epsilon. And the distance between populations will be zeta. And I'd like to understand what happens if you approach the frontier with epsilon, delta, epsilon, zeta go to 0 as n grows, for instance. So I show just the final result, one final result, and I will discuss all this. You don't need to understand everything in such a slide at the first glance, but first I say that there is an L over there. And this L just comes from the fact, I will not discuss it here, but from the fact that in your using of empirical means, if you want to build estimators, then you need some mixing, and this is the absolute spectral gap of the Markov chain, so that you'll be able to mix a lot, which means that if one of those is small, when you have sparsity, it's only one of them to be small, not both. we do not approach the periodic case. Then the result is that here are the constants coming in front of the estimator. So you see here they are the same for P, Q, and F0, F1. It means that with large probability, those estimators, the distance to estimators, are upper bounded by those rates. And you see that if n, it's around L, n delta 2, epsilon 4, zeta 6. No, here you don't have the same, but depends on if your zeta, well, it's not exactly the same rate, both depending on which one. And we have lower bounds with the same rates, where you recover the maximum and here, and the zeta 6 and the zeta cat here, which means that if this is too large, larger than 1, then you cannot recover you do not have consistent estimations. So I will explain now where all this comes from and how you can understand the behavior of your hidden Markov in this very simple situation of two hidden states and multinomial inequalities. So the key thing will be, as we've seen on identifiability trick, we just have to look at the 3 consecutive observations. And if we understand how it behaves regarding all those parameters, we hope to be able to understand what happens. So we'll change parameter, and this, well, you cannot, well, I write down the parameters. Each one will be related to the boundary. So for phi 1, just being near 1 or not. So in fact, you have I don't remember exactly, but it's something like delta. Phi 1 tells you about sparsity. Phi 2 tells you about, well, I think we changed the sign, and I didn't change the slide, but not very problem. Phi 2 tells you about being near independence, about the determinant of Q, and phi 3 tells you about the separation of populations. And these are parametric things. And then you have things related to your densities, and the first one is the stationary distribution. This is the easy one because this is the distribution of one observation, so you know you can estimate it as soon as you have mixing at the rate, at the usual rate. And then this one, the second one, is more intricate to recover both situations. So here we have phi 2 telling the story about epsilon, and phi 3 about zeta. So the situation you want to investigate is the situation where phi 1, phi 2, or phi 3 is near the boundary. Is near phi 1 is near 1, or phi 2 is near epsilon, and phi 3 is near z, is near 0. So if you use the tensor trick, if you remember it, you write the distribution of 3 consecutive observations as a mixture of 2 populations in which you can factorize, and in the middle you have your emission densities. And then on the left and on the right, you have other things that come from your emission densities and your transition method. But then if you write it using this new parametrization, then something nice comes out. It is the fact that the first term is, so here in the indices, it's taking independent psi1, then psi1, then psi1 again. So here you have psi2 and psi2 and psi1 with tensors in which. And the first term is, if you don't have the other ones, is the distribution of three independent variables having the invariant distribution as a distribution. So indeed, it is the distribution of your data if they are independent. If they are no more dependent, then here, this is your distribution of three consecutive observations. So the remaining is what comes from being near the boundary or not. And in the remaining terms, something factorizes, which summarizes how far you are from the boundary. There is this term telling how far you are from delta, from the boundary delta, this one about epsilon, and this one about separation of populations. So there is this square. So you know, they do not play the same role. Yeah. This is here. So this is why I put it on the board. So this is the stationary distribution of your observation. And this is the other one that allows to go back because it's invertible parametrization. And it says the direction of the difference. It's a normalized. And then, so if you look at this, you see that we have three terms. R of phi, phi2 R of phi, phi1, phi2, phi3 R of phi. And in fact, this will be the key parameters telling the story about the rates and the constants. That is, you can prove. So I named them M1, M2, M3, but they are just what comes in front of each. So you have R of phi in each. But then you multiply by something, so you have three terms in your remaining term. And this is what tells the story about what you need to understand rates, because you can prove that indeed this is the distance between parameters that explains well the distance between three consecutive distributions of three consecutive observations. So you can call it some statistical distance. It is not a distance, it is a pseudo distance. But since you have equivalence, so at least in the multinomial case, but at least for the lower bound, we are able to extend it to the non-parametric situation. There are constants, but here, those in this, the hidden constants, of course, do not depend on parameters. And they depend on the, for instance, in the multinomial emission things, they depend on the number k of possible here. But you can extend to densities on compact set, and they will depend on the size of the compact set. So then je ne sais pas si on voit le bas. So it's possible to learn the distribution P3 empirically. And then you can, for instance, estimate the parameters phi and psi by minimum distance. And then use this equivalence to go back to your parameters. So that's what we've done. So just it's just written down here. You estimate empirically your 3 consecutive observation distribution. Then you choose the parameter which is closest. So the parameter should be here also. When you describe your 3 consecutive observation distribution using hidden Markov with those parameters, you estimate those parameters. And then you go back. And then you get rates. And here you see that you can get rates individually for each parameter. And because of this equivalence between all parameters, and we wrote together, because you estimate things that are small, we decided to write also rates about ratios so that they are more meaningful than just absolute rates. So then you get different rates, you see, for ratios because of course and for all things. So these are upper bounds for the size. So you see that there is nothing about the stationary distribution, but here all the difficulty of the part about emission distribution is in psi 2, because here you have constants that depend on the boundary. So now I come to lower bounds. No, they have k. The same about what? The same as what?
Same constants.
So the constants here. So here you have the C here are the constants that come from the constants that I did not show here. Because in the empirical means you have absolute constants here. Well, here you have the absolute spectral gap, if you write it this way. On the board I have put it here, but you can put it here. You have thing about the mixing, but not on the boundary either, on the dimension of the space or anything. The constants that can depend on k or on the width of your compact set over which you take densities come from the equivalence here. Because you invert this exactly. You use the upper bound here on the empirical to get upper bound about this, and then you go back from m to phi. You invert m to go back to phi. About square root or what? No, it's more than square root. It's more. But you can do it for continuous densities in which it's not, well, it's not complexity as a number of observations. It's just the width of the interval. It's larger than square root of k, I think so. What a bit. Yes, 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 of course. But, well, we are writing down it now. We're not finished. But hopefully we can do the adaptive story, etc., etc. But we get the rates depending with the same constants. We find the same constants. Because in fact the constants come from some parametric thing here, you know. It's about Q and just the distance between densities. The constants will not depend on the smoothness. It's only the rate. So, bon, je ne sais pas comment on dit en anglais, je vends la peau de l'ours, mais as usual, I sell the, how do you say in English? As usual, so we are just working on that for the moment, but I believe it's here, in the non-parametric story, it's here in n that you'll have a power depending on the smoothness, but the constants here will not change. So now I come to lower bounds. So who knows who it is? Oh, LeCam, it is LeCam. So LeCam is one of the great statisticians of building statistician theory, but more in the frequentist ideas, you know. And I want just to explain. So there is a paper by Bin Yu, I don't remember exactly when, in the 90s, I think so, Bin Yu. She wrote a paper explaining the ideas of LeCam and how the 2 points lower bound comes from his ideas of testing between 2 points to get lower bounds. So it is a very, very simple thing I can write in 3 lines on the board, so I will do it. But it is very powerful since it gives in many situations, it gives you the opportunity to get, so it's in the 70s again. So I write the name because I don't know if everybody knows this here. So he's French, but he worked in Berkeley. He's a French statistician. So it's a very general, so you want to estimate some parameter u, from which you have information with some y, with distribution depending on u. So of course you could have other parameters, but I would consider only what happens with u. So you assume you have some loss function and 2 points such that, and a constant such that there exists a constant such that for every t, the loss between u1 and u2 is upper bounded, something that looks like a triangle inequality. And here, you know, the order, the loss function can be not symmetric, can be not a distance. It just has to verify this and be non-negative. So remember, I had this ratio when I want to prove rates, not only for absolute rates, but for ratios. But here it's not symmetric because it can be u1 over u2. It's not symmetric, so it's important the way you write it. So assume you have that, and the total variation between the distribution is not too big, smaller than strictly than 1, then if you take your minimax risks, of course you need that your 2 points be in the set of parameters you want to investigate. Then your minimax risk is lower bounded by this c, no, y minus small c divided by 2 large c. L de 1 et 2. I forget this one. So this means that as soon as you find large this loss between U1 and U2 for distributions that are not too far, then you have a lower bound for your minimax risk. And the proof is one line. So since this does not depend on data, you integrate it using the infimum between. So when you have two probabilities, you can define densities, for instance, with respect to the sum of the two. You integrate it with the infimum. Then, of course, you lower your upper bound using this inequality. So you have C. But then when you integrate U1 with T, you take the upper bound for this as PU1. And then you do the same for the other, but of course you choose PU2. So you see that this is less than 2C, your maximum risk of your estimator T. And here the lower bound depends here. This is exactly equal to, because there is nothing random here. And this is the testing distance, 1 minus, so you can prove it's not difficult, that it's related to total variation distance this way. And then, if this is small, you lower bound using 1 minus C, then you have a lower bound for your minimax risk. So this is a very nice and simple idea that become hard. Of course, then you can build on this idea to have more testing bounds, and there are more strategies if you cannot apply these 2 points lower bound, but for us it did work. And now, if you have a sequence of observations, then here what we need is to understand the total variations between, I'll put it here, and it will be the last. Total variation when we have consecutive observation. And then you can use Pinsker. So this is what we do. Use Pinsker. Inequality. Bond it using Kullback. The Kullback distance between and consecutive. And even for independent observations, total variation is not easy. So you have upper bounds with chi-square or Hellinger or Kullback. You use the one which is the best in your situation. So now the end of the story in the hidden Markov comes this way. So we did this in our situation. So this slide just says that you can use the loss function, which is a ratio, and then you have, well, I think 1/100 is a bit too much, but too small, but it doesn't matter, just numerical constant. And then what remains to do in our situation is to understand upper bounds, because of course, of Kullback, because when you have independent observations, Kullback of tensored densities, Kullback information, divergence, some sums, it's just a sum. But in our situations, it is not. However, it's possible to relate Kullback to have an upper bound, because here, of course, you see that since you want to have a small upper bound for your total variation distance, you need, if you want to use Pinsker, a small upper bound on your Kullback divergence, and we were able to get an upper bound related to the statistical distance I talked about just earlier, which is the right statistical distance about the 3 consecutive observations. And this has the flavor of the IID situation, in which you have this, the number of observations and something relating the densities. So this upper bound holds if you have a lower bound on densities, and well, it's in the neighborhood of the limiting IID situation, but it's in a range that does not depend on n anyway. So how do we prove it? So instead of saying that you have tensor distribution, you write the Kullback divergence as the expectation of the log likelihood ratio. Then you write likelihood of y1 till yn as the product of the density of yj given the previous y's, and from j going from 1, well, it's k here, from 0. So that it adds up is if you have the product, then for taking the logarithm, it adds up. So you have here Kullbacks of conditional densities that adds up. And then for each of these Kullbacks, we use chi-square upper bound of Kullback. And then we write the conditional distribution of an observation given the path using, so I do not need that anymore, using the dependent structure. If you take this as the marginal over y of yk plus 1 and kk plus 1, and then you condition using xk plus 1, then you lose the dependence on the previous observations as soon as you condition on the state. So here you just have the posterior probabilities of each state given the path of the state, which are called the predictive probabilities. So those ones, if you assume some lower bound on these functions, is lower bounded also, because you can write it as a mixture. And then you rewrite everything using our new parametrization. So here it becomes more technical. But you can write it using the parametrization, and just one thing comes out. It is this one that makes only appear the prediction probabilities. And then what's nice with the prediction, so it's the one you have to handle. The thing you have to understand how it behaves, how it evolves, if you want to have a nice upper bound. But the nice thing with prediction probabilities is that you have this forward equation that says that they satisfy a recursion. So this is a simple recursion in which you have only the transition density and the emission density, so that you can work with it. You write it for what you need, and then you work with it, and then you can prove by induction that it's upper bounded what you want. And at the end, you get the upper bound for the Kullback divergence between your n-dimensional densities of observations. And to end the story, you use the 2 points lower bound from Le Cam. Yes. Because you just need that it be satisfied for the 2 points you choose. You mean this one?
Yeah.
It will be, you know, we take 2 points. We only take 2 points. We do not need that it satisfies by the whole set of views. You just have to take 2 points. So did I put it in here? We just take 2 points, only 2 points, for which we can prove this upper bound. For those 2 points, we are able to prove this.
What can you say about that?
Because here you take the t on the numerator. It's the you write u L of u1 u2 as u2 over u1 minus 1. You don't write u1 over, you don't write u over t, but t over u. It's not symmetric. Pardon? No. We choose the 2 points. We don't take any 2 points. I don't understand your question.
How do we make?
Pardon?
We make.
Oh, yes, you take some time and you think hard about it and you choose them. So it's the difficult part of the proof to find the right points. And sometimes 2 points are not enough. So you're lucky if 2 points are enough. So we were lucky for that. But it took us some time to find the points. Okay, I didn't understand the question. Thank you. For this specific thing, in general, what you try to do is to get as large as possible this while keeping this small. This is the idea, but well, this is a very general idea. So in my problem, I wanted to take points as close as possible to the boundary, on the part of the boundary where we were estimating the parameter. This is why we get lower bound individually for each phi's, because for instance for phi 1, so I can show, well, I don't remember if I put on the slide how we choose. But you know, this tells the story. If you want to estimate phi 1, you try to find some phi 1s, so the tilde is for the 2, such that you are close to the boundary, but you're very close to the boundary, so both are. But then, so it's not here, or they are close to the boundary. Here it's, well, then you have this as large as possible. This is this. So having this small, and because of there. So it's not very precise, but this is the idea. So we use the Le Cam argument, and then, for instance, for phi 1, this is how to do, and then this gives individual bounds, lower bounds for each parameter. So this is the end of what I wanted to tell about the fundamental limits. So we see how the rates are deteriorated when it becomes sparse, or nearly sparse is delta, nearly independent is epsilon. The emission multinomial becomes closed, it's zeta. So the way to do this was to identify the right statistical distance. Then we are now just extending the story to the non-parametric setting. So I'm quite sure that everything goes through, just the rates, of course, become adaptive rates about estimation, smooth densities, and so, but the constant will not change. So I believe that if you have more than 2 latent states, well, I don't know if I will be able to do this, but this is still a question, because in the 2 states situation, there is this nice understanding of how you can do the reparametrization, but here when you try to understand when Q becomes non-invertible, well, it becomes more difficult. And then there is still the question. I said at the beginning that all this was to understand when you have data, if what you will infer from your data holds true or not, because you don't know exactly how much independent or dependent you are. So this is still an open question. We have the rates, and now we have to put it in action to understand how your uncertainty quantification can be safely said on what you will say about whatever clustering or Bayesian multiple testing or anything you have in hand. So there is much still to do on the subject. So these are the things I'd like to work on, but there is a lot of things to do. So I still say that understanding the frequentist Bayesian story for Bayesian multiple testing, the guess is that you could have weaker signals to detect sparse structured sequences, and for this we needed to investigate the delta that goes to 0. Sparse is when delta is small, when the phi 1 is near 1. Then there is the question, the general question of if you have dependent data and if you want to make population mixtures and you believe you can do non-parametric things because you have dependence. This is the very, very general question at my very first slide, which is just for a general idea, but how can you say more precise thing about those stuff? For instance, if you use hidden Markov, it can work for dependent data, but how much? Or do you have to adapt your hidden Markov to adapt to dependencies or whatever? So this is the last point. So thank you. This is the end.